Friends, so far we have understood that how to identify the geometrical isomers and optical isomers in alkenes, cumulated dienes, Spiro compounds and triphenyls systems just by two simple rules. We have learned just two simple rules, and these two rules are applicable in all these four systems. It is very interesting, isn't it? So now we are going to see the optical and geometrical isomerism in cyclic compounds. We are going to learn geometrical and optical isomerism in cyclopropane, cyclobutane, cyclopentane and cyclohexane. So let's move forward. Geometrical isomerisms in cycloalkanes. What is the reason that cycloalkanes are showing the geometrical isomerisms? This is because rings up to the 7 carbons have restricted rotation about carbon-carbon bonds. So due to the rigid structures of the cycloalkanes up to the ring number 7, they have restricted rotation, and hence it can show the geometrical isomerism. And due to the angle strain, the stability order is 3-membered ring is less stable than 4-membered ring, and 4-membered ring is less stable than 5-membered ring. So 6-membered ring is more stable as compared to the smaller ring sizes. Now let's look the geometrical isomerism in cyclopropane. Cyclopropane can show the geometrical isomerism if it is 1,2 disubstituted. So this is, let's say 1, this is 2. So this 1,2 disubstituted cyclopropane can show the geometrical isomerism. So this will be cis when you have 2 methyl in the same side, 2 methyl group are on the same side, and trans when 1 methyl group is opposite to the another one. And these cis and trans are not interconvertible at room temperature because of the restricted rotation around carbon-carbon single bond, and hence all the 1,2 substituted cyclopropanes can show the geometrical isomerisms. So therefore the question comes, how many geometrical isomerisms are possible for 1,2 dimethylpropane? So there are 2 geometrical isomers, one is cis and trans. And now to find the optical isomerism, as I told you, you have to look the plane of symmetry. So cis compound has plane of symmetry, therefore this is optically inactive. Cis is optically inactive, but trans doesn't have plane of symmetry, so it will have 2 enantiomers. Therefore total stereoisomers will be 3. 2 is geometrical isomerisms and 1 is optically active enantiomers. Most of the students get confused because they are thinking 2 geometrical isomerism plus trans is showing 2 enantiomers, and then the answer should be 4. But this is wrong because trans is already counted into one of the enantiomers here. Okay, so trans, for example, trans 1R, 2R is already counted, and then its mirror image is 1S, 2S. So therefore it is 1, 2 and cis geometrical third. So it has total 3 stereoisomers. Now let's move forward. If you have such systems in which, let's say this one is 1, this is 2, and both substituents are different, in such a case you will have, this is cis when you have same, these groups are on the same side, and this is, you can call trans because methyl is opposite to the amine group. This is also not interconvertible into each other because of the restricted rotation, and hence you have 2 geometrical isomers for these compounds. Now what about optical isomers? So if you look this cis, can you divide into 2 half? No. So cis doesn't have plane of symmetry, no plane of symmetry. Therefore it will show the optical isomerisms. So cis is going to show the optical isomerisms, and similarly trans doesn't have any plane of symmetry, therefore it will also going to show you optical isomerism. Now again there is a confusion, Students used to make mistakes. They are thinking 2 geometrical isomers and 4 optical isomers is equal to 6. But this is wrong, because we have already included these geometrical isomers, so we cannot add separately. So cis will have 2 enantiomers. What are those enantiomers? So one is, for example, you can see here the configuration is given 1s 2r, one is this, and its mirror image will be 1r 2s. Similarly, trans will have 2 enantiomers, and that will be 1r 2r and then 1s 2s. So therefore, if you count it, therefore it is 4 stereoisomers. How many stereoisomers? Total 4. And in the previous case, total stereoisomers were 3. Now let's move forward. Geometrical isomerism in 4-membered ring cyclobutane. Cyclobutane actually exists in the U-shaped. This is U-shaped because of the angle strain, or we can say ring strain. It is existing in this shape. So when the molecule is given like this, so you can write it down like in this way. 1 bromo is above the plane and chloro is below the plane. This is one chiral center, this is another chiral center. So bromo is on the same side, therefore this is cis, and again these are not interchangeable. And now in this case bromo is below the plane, and here is also bromo is below the plane, so this is also cis, and they are same. So there is a mistake in drawing this structure. Actually it's supposed, for trans it should be like this: bromo, let's keep up with the plane, chloro down the plane, then this chloro is above the plane here, and in this case bromo is down the plane. So this will be trans. So this is these are not interchangeable. So actually we can say that structure A and B are same. So we can say that these are same, because if you rotate around this axis, just rotate around this axis like this, then this chloro will come above the plane and bromo will go down the plane. So this A and B actually same, identical. So trans will be this one. So it has 2 geometrical isomers. What about optical isomers? So cis, if you say, you can see that cis has plane of symmetry. This implies that no optical isomers, but trans doesn't have plane of symmetry. No plane of symmetry. Hence trans can show the optical isomers. So trans will show 2 enantiomers and one is cis here, so total will be 3 stereoisomers. Okay, now let's look at this structure in which this is 1, 2, 3. 1, 3 disubstituted cyclobutane. Here you can have also 2 geometrical isomers. The first one in which NH2 and methyl are opposite, so therefore this will be trans and this will be cis. And again these are not interconvertible through rotation around carbon-carbon bond because of the ring structure. So it has 2 geometrical isomers. What about optical isomers? Now let's look the plane of symmetry. So if you see that you can divide this molecule into identical half by passing this plane. If you pass this plane, then you can divide the molecule into 2 identical half. So trans and cis both have plane of symmetry. So therefore there is no optical isomers because cis and trans both have plane of symmetry. So therefore, there is no optical isomerism, only two geometrical isomerism. Now let's look the 5-membered ring. In case of 5-membered ring also, you can have 1,2 disubstituted ring, and you can have this kind of structure where you can say it is cis, and when this 1,2 substitution are on the opposite side, then you can call it trans. And cis has plane of symmetry, therefore cis is optically inactive, but trans is optically active, so it can show optical isomerism. So trans will have 2 enantiomers, so total stereoisomers is equal to 1 is cis, which is optically inactive, plus trans have 2 optically active, so therefore total is 3. What about 1, 3? Let's say if you have OH here and OH here, so this is 1, 2, 3. So in this case also, this is cis, and you can draw the transform of this. So one OH is above the plane and one OH below the plane, so this is the trans. And again here you have, let's look, this compound can be divided into 2 identical halves, so it has plane of symmetry. What about this compound? If you try to divide into 2 halves, so we cannot divide by this plane. What about this? Can you divide into 2 halves? No. So trans, no plane of symmetry, therefore it is optically active, and this one is optically inactive, and hence total stereoisomer is equal to 3 in this case also.